it's roughly the same proof, but it's just done by contradiction. So that's also fine. And if not, so this is only half the story. This is what I want to highlight, because an algorithm could always reply yes, and it would satisfy this property, right? That if the path exists, algorithm returns yes. So what we should also prove is that if there is no path from U to V, then algorithm returns no. So if there is no path, this in this case is actually very simple, so I'm not going to go into the proof, but can someone try to give a hint of how you would prove this? So let's look at that. Oh, sorry. Okay, so if there is no path, I want to say that the algorithm returns no. So, and is that clear?
To reach that path, we have to go to a path which is not accessible by the previous path.
What do you mean to reach that path?
So in the previous example, you gave U1, UK minus 1, UK and V. So we just go one step back and prove that we will not be able to reach U1 by the path that we have taken so far.
Yes, but now there is no U, V1, V2, so on, right? Because there is no path. So, so earlier we started off with assuming, okay, let's look at this U, V1, V2, up to Vk. Right? But now there is no such path.
Yeah.
So, how are you going to prove that? Yeah.
You can probably do it by contradiction. So
okay.
If it returns a yes,
okay,
there is clearly a series of explore.
Okay.
So which means there is a path.
Yeah, so that's one way of showing it. So, yeah, so anything else? Any other?
No,
yeah.
We can assume a broken path.
Okay.
Like a path but in a hole in the middle.
Okay.
And then we can keep showing that it reaches till the end of the hole and then it does not cross the hole.
Well, those kind of things are hard, right? So that's like saying you are showing that instead of showing V is not marked yes, you're showing that somebody right across is not marked yes. Right? So that's as difficult as showing that V is not marked visited. Right? So, yeah, so any other? Yeah.
You can take an isolated vertex and prove it. I mean, since the vertex is isolated, the algorithm won't go through the for loop since it checks for all the neighbors, and only that vertex will be marked true. So,
sure. So if U were isolated or if U is isolated, then this is definitely, that would be an argument. But you could have some edges that go out, so it will do some exploration. And we aren't sure.
You should be able to go back recursively if you assume that you
algorithm returns no. Right? The way we are proving that is by saying for any path that was marked, for any vertex that's marked explored at the end of this function call, we can trace a path back to you. Okay. So this is what I want to claim, and the way I am formally proving it is by saying, okay, so this is the formal claim. And the proof is that if a vertex, so let's call this vertex x. So if a vertex x is marked explored and x is not equal to u, so if x is u, the statement is trivially true, then there should have been some neighbor of x that was explored first, okay, and that would have triggered calling explored of, that would have triggered setting explored of x. Okay. And and this happened at a previous time instance. Okay. Then you can say that somebody else in a previous time instance should have triggered this, and so on. Now time was only finite, and at time equals 0, only u was explored. Okay. So there should have been a path that went all the way back to u. Okay, so that's the really formal way of doing it. So this is this is just to illustrate to you that if you want to really formally reason about things, sometimes it could be complicated, but you should at least know roughly what you're trying to argue. Is that clear? Did I answer you? So maybe you might want to think a little bit more about this because many of these proofs, right, unless you actually reprove them to yourself, you don't quite internalize them. So I would encourage all of you to go back and try to do the same. Okay, so this is, I'm not going to go through this in detail because to get to some other stuff, but how would you analyze the running time of this algorithm? So again, this is the algorithm, right? So if you start with explored of u, you do this. How would you go about analyzing the running time? So, and what's the reasoning for that?
So you're doing a single loop and you're just iterating through an adjacency of the list. So just be of n, right?
But you have recursive calls inside. So this is true, right? So for any function call, it is true that you only explore all your neighbors. So if you had so if the degree of u was d, then you just explore d different things. For each one, you call a recursive call. You make a recursive call. And you've got to show that recursive call, I mean, how many times does this happen, and so on. Right? So you got to analyze that. Yeah.
This algorithm will enumerate all the aspects in the graph, so I think the runtime is of n plus the size of the edges.
Yes, and why is that? Why do you think? So when you're saying that the runtime is the number of edges, roughly proportional to the number of edges, you're saying that every edge is explored, but every edge is also explored not so many times.
They are all enumerated for each of the edge.
Yes, and why is that? So why is each edge explored exactly twice? Or firstly, is each edge explored? And if so, so that's what we've got to ask. Right? So there might be some edges in the graph that are not explored at all. Like if you have two disconnected pieces, you probably never explore edges out here. Okay.
So in the worst case, I think we will be visiting all the nodes, because while we are recursing through the neighbors of a particular node. If that is already explored, we don't go back.
Okay, so that's a key observation, right? So the observation is this function called explore of u or explore of some vertex x is called at most once for every vertex. At most once. And when the function call happens, what time does this call take? Like just the call to explore of x. So each call takes time O of degree of x. And this is the argument, right? So if you sum up all the degrees, you get twice the number of edges, precisely as she said. Okay, so that's one of the explanations. But it's important to note that this is an upper bound. Okay, so there might be some vertices which you don't even explore because the graph is disconnected. Okay, so this one, this is a small exercise for you. I won't write this down formally, but that's roughly the idea. Okay. Any questions on this? Yeah, but the main idea is what you mentioned, that the function called explore of x is called at most once for every vertex. Okay, so these are the kind of things you've got to observe about an algorithm.
So how would you like classify that word over time or word subprogram? I mean, this is just the verbal.
Right. So now you say that let's look at the entire running of the algorithm until it ends, right? So what she said is that explore of x is called at most once for every x, and for that x, the function call takes time at most O of the degree of x. Right? So the total running time, you can say, is it's in total time. Actually, I have a slide for this. Right? So total running time is less than or equal to sum over all x. Okay, so the sum over all the vertices of degree of x. Because for every x you call it at most once. And did you have a question? Yeah.
But when we consider the worst case, it must be a fully connected graph.
Yes.
So the times that we call the explore function is only n times, but the times that we enumerate all the others in each function is also n. So the number of edges that we enumerate could be n times n.
So that's where I did something tricky, right? So I did not. So yes, what you said is a perfectly valid argument. So you're saying that this step you could say is at most n. But I'm saying something stronger. I'm saying that it's at most the degree of this vertex u, which could be significantly smaller than n. Right? Does that make sense? So I'm saying that the number of neighbors of u, it's a degree of u. So this is a number that's definitely smaller than n, as you said, but it could be significantly small. Okay? So that's why I'm hoping that gives me some advantage. Okay, so that's why I have bounded it as the O of degree of x. Okay, and those are the quantities that I will sum. And what do we? Yeah, so that's a good point. It's so very often if you do analysis with one bound for a certain quantity, you might get a slightly different overall bound, which could be weaker or stronger. And so that's why it's important to be as tight as possible whenever you can. That's a great question. Okay, so alright, so this is what we have. So total running times at most is. And what's the bound on this? Yeah, so sum of degrees in any graph is 2 times number of edges. So you could write it as this. And that's it. Right? So this is the bound on the number of times. Okay, so the algorithm has running time which is 4. Okay, so if you want to be really formal, you might want to put +1 here because function call always takes some time. Was that what you were saying?
No.
Oh, no. Okay.
I had that. So, number of nodes is n, right?
Yes.
So, is 2 into number of edges that can be greater than number of nodes?
Yeah.
Yes. Typically it is.
It is,
Yeah.
right? So,
Yeah.
would that be a title bound or this? I mean, I don't understand the notion of title bound. You say.
Oh, so like n squared is always an upper bound on the running time, right? So you could say it's O of n squared, but I'm saying that 2 times number of edges plus n. Like if I have that +1, then I would get something like this, right? So this is a tighter bound because number of edges is always less than or equal to n choose 2, which is less than or equal to n squared by 2. Okay, so this bound is always better. Okay, so for that reason. So that's what I mean by a tighter bound. Okay, any other question?
So in this case, if we had a homework that asked this, would you ask for the 2 times number of edges plus n, or would O of n squared be okay?
Yeah, so you'll get partial credit if you have O of n squared,
Okay.
but to get full credit you will need something. Yeah, usually I will specify.
Okay.
I mean, I will specify, come up with an algorithm which has this and this bound. Sometimes I might not specify, I might just say give a polynomial bound. In which case I don't really care if it's n squared or something like that, so you'll still get full. Yeah.
So where did you get 2 times the number of edges again?
Oh, the sum of the degrees. So for in any graph, if you look at sum of x and v degree of x, right? So what is the summation doing? Right? So it's for every vertex you're adding up the edges that go up, the number of edges that go out of this vertex. Right? And in this process, yeah. So as people are saying, every edge is counted precisely twice because once it's counted here, once it's counted when you're counting the degree of this vertex. So that's why it gets counted twice, and everything is counted precisely twice. So that's 2 times. Good. So, all right. So let's move to what I wanted to do today. Okay, so today I want to talk a little bit about divide and conquer. Okay, so this is an old concept, right? So people have used it for devastating effects. So, but what we are trying to do is something much simpler, something easier to follow. So what we are trying to do is you have a problem that you want to solve, okay? And the idea in general is you break it up into a bunch of smaller problems. Okay? Very often, how you define smaller is important. Okay, but in the examples we'll see, it will be natural. Okay, so there will be a natural way to divide the problem, and you solve each part separately. Okay, and the important thing is that you don't think of the other parts when you're solving this subproblem. So that's how it's solved. Right? And then you somehow combine all these solutions to get the solution to the full problem. Okay, so this is just a very abstract way of describing divide and conquer. We'll see some examples. Okay, and what you typically want to think about when you're solving a problem like this is you have to figure out how you divide the problem. Okay, not every way will be very meaningful. Okay, so sometimes the way you divide things will actually, affect how quickly you can solve things and so on. Okay, so how to divide is something you should think about. Okay, and we typically solve the subproblem recursively. Okay, so that's one easy way to solve this. So that means you break up each subproblem into smaller subproblems and so on until it's so small that you can just read off an answer. Okay, so that's typically what we do. Typically recursively. Okay, and the most critical thing in all the examples we see is the conquer step, right? It's like how you put together solutions for these various subproblems to come up with the right solution to the. Okay, so this is where you've got to show that, you've got to prove that this is done correctly. Okay, so sometimes you can just come up with some way, a natural way to combine things, but it might not be the right answer. Okay, so this is where you've got to be careful. And we'll also see how you analyze the running time, especially if you do things in a recursive way. Okay, so this is what we'll look at. And I'll do it kind of in a few different settings. Okay, so we'll get some sense. And what we want to get a sense of is when you can actually use this kind of a paradigm, okay, this divide and conquer paradigm. And hopefully, and I'll point you to some resources where you can read a bit more about divide and conquer. Okay. And yeah, so ideally we would want to pick subproblems that are simpler. Usually they'll have a smaller size, but they could also be simpler in other ways. Like maybe it has smaller number of edges or something. Might have the same number of vertices if you have a graph problem and so on. And ideally, this is obviously something we need because okay, so combining solutions should be easier than solving from scratch. Okay, so these are the kind of places where you would want to use divide. Okay, and as I was saying, we'll look at 3 examples. So in the first one, it will be natural that you have to do some kind of divide and conquer. This is something we would do naturally in life. And we'll see another problem for which it's reasonable, and another one for which it's a bit surprising that divide and conquer works. So those are like the 3 examples we'll see. Okay. So the first example is finding your way in a map, right? So this is a map of Venice for those who didn't recognize, and yeah, so suppose you want to get from one place to another, right? So let's say I want to go from here to here. Okay, why did I choose Venice? Because it has all these canals, and you only can cross a water body when you have a bridge. I mean, if you're walking. So let's say you want to go from there to here. How would we naturally do it? You would observe that, oh, there's this big canal that I need to pass. And there's only 1 or 2 bridges here. There's a bridge here if you can't see. There's a bridge somewhere here. So you'll say, okay, I was there, so maybe I want to get from here to here. I'll solve this subproblem. Then I'll cross the bridge, and I'll solve this subproblem of going from here to here. Right? So these are the kind of situations in which you will naturally recursively solve a problem. Because then you'll say, oh, okay, but on the way from going from here to here, there's a lot of water bodies. Could I identify the bridges here? And maybe go from here to here first, then from here to here. This is what you would not typically do. So there's some problems in which divide and conquer is what we instinctively do. So another example which you probably have seen, hopefully all of you have seen merge sort. Okay, so here you have an array of n numbers, okay, and your goal is to sort them. Actually, how many of you have not seen merge sorts before? Okay, great. So I'll just briefly explain what it does, just to refresh your memory. Actually, that's probably a wrong question to ask. I should probably just ask how many of you have seen it. But okay, so all right. So the way merge sort works is as you would expect. So you have a bunch of numbers. Each square corresponds to some number. So you have A1, A2, so on. Okay, and you break it up into 2 halves. Okay, and you sort these halves recursively. Okay, so this is the first problem. This is the. So go back to the picture, right? So I'm just dividing it in a most natural way. the way the array is written into two halves. Right? And I'm just sorting, so this is this array, and now I will sort this. And how is this sorting done?
Calling the not sorted.
Yeah, so you do this recursively. Okay, so this we won't write, but what this intuitively does is break this into two halves again, calls it on these different parts and so on. Okay, so this is how my sort works. And now you get a sorted array here, you get a sorted array here. This is an increasing order. Okay. And now you've got to combine these things to form a single big sorted list. Right? And the idea behind merge sort is that somehow you can do this process pretty efficiently. And so what's the time for doing the merging?
Merge is log n.
Yeah, so n log n is the overall running time. So if you have two half sorted lists, right, or two half lists that are both sorted, how long would you take to? Yeah, just n. And how does it work?
You take 2 pointers on the head of the
Yeah, so this hopefully all of you have seen. So what you do is these are both sorted in increasing order. So you will. So the smallest number out here is the smaller one of these two. So you write that over here, and then now you have this list and you have this full list, and so on. Okay, so you have 2 pointers that move forward. Hopefully, yeah, you can look this up. So this is very easy. Okay, and this takes O of n time. Okay, to do the merging. This will notice that the overall runtime I'm shooting for is something like n log n, but this combining the solutions part is actually significantly easier. It's only n time. And that's typical in all these divide and conquer algorithms. Okay, so the conquer step will be easier than solving the problem fully. This is what you do. Okay, so again, here formal proof is kind of obvious, right? So, but if you really somebody put a gun to your head, how would you prove? How would you write down a proof? Wait, somebody else. Yeah, somebody from that corner. Alright, it's fine, yeah. So
each of the smaller arrays are already sorted, so when we are merging it, so we are always putting, comparing it and putting it in increasing order. So, the merged array will be sorted because we are comparing between sorted arrays and putting it again in increasing order.
okay, so yeah, so that's the right idea. And basically what you have to say to formally state is that, should say that, okay, so you can assume inductively that the recursive call to merge sort actually correctly sorts. Okay, so the proof is officially by induction. And what you essentially said is there are 2 steps, right? So one is the sort on the subarrays works correctly. Okay, so this produces 2 subarrays that are both sorted. And then you are saying that the merge step returns a sorted list. So this is perfectly the way to argue about this. So basically, you see what the algorithm is doing. You say that, okay, inductively I can assume these things are correct. And now the merge step, this is the only step I have to prove works correctly. Okay. And this, as you were saying, is correct because you always take the smaller of the 2, and if you really want, you can argue this also formally. Okay, so we're not going to do that. But this level of observation is fine. right? So that the merge step, these are the two steps that you have to kind of prove. Okay, so you should be aware that this was going. Okay, so let's not go into that, but let's actually look at the running time in a bit more detail. Yeah, because this will give you an example of how to solve recurrences. So I'm going to do this. Okay, so how would we write down the running time of such an algorithm? Okay, and this is what you would do for typically for recursive algorithm. For divide and conquer. Okay, so how would you write down? Okay, maybe.
For a sorted array of n and n size, the merge procedure takes n, and there are log n levels because we are breaking into half. So for each level, though the number is decreasing, like for the last one there will be n by 2, n by 2, and the following one there will be n by 4, n by 4, n by 4, n by 4. So there will be in all the levels log n into n.
So you're saying, okay, so you're actually doing it, you're writing out the recursion. So let me do that. So you're saying there's one problem of size n, which you start out to solve. You're saying, okay, we solve two problems of size n by 2 recursively, and plus there is an extra work of n. Right? And now this one you're saying, okay, so now we solve two problems of size n by 4, n by 4. Here also there's an extra work, right? But this is now n by 2. Okay, so extra work n by 2, okay, and so on. Right? So this is fine. You can write down. And now what would you do to analyze the final running time?
So for each level, I need to count the number of levels.
Yeah. So you have the number of levels being log n.
Yeah.
Right? Because here. Okay.
And each level, the extra work for first level is n, for the second level is also n by 2 plus n by 2, that is n. Again n by 4 plus n by 4, so that sums up to.
One would solve recurrences, but this, yeah, you'll see it gets a little trickier to do. So it's better to first write some shorthand, okay, and that's what these guys probably say. So you could say that, okay, let me define a function. Okay, which is t of n, supposed to be the runtime for an instance of size n. Now, what you said exactly is like saying t of n, the way it works in our algorithm is that it is 2 times t of n over 2 plus this extra work of n. So that's what this does. And when you try to expand this out, this is exactly what you get, right? So when you say this is like 2 times 2t of n by 4 plus n by 2 plus n. So this extra word part always evaluates to n. Okay. And actually to compute this recurrence, this is exactly what you would do. Okay, so you would unravel this recursion tree, as they call it, okay, and you would just combine all these the terms that don't have the t. And you should also be a little careful about what happens in the base case, right? So you've got to see how these terms evolve. So first it was 2 times t of n by 2, then it's 4 times t of n by 4. Eventually you will get n times t of 1. Because it will be n by 2, n by 4, whatever, and eventually it will be n times t of 1. T of 1 is 1 in our case, so that's equal to n. So there could be problems in which you need to stop at a slightly higher level, but that's fine. That's how you handle these terms. Okay. And all these extra work steps add up to n in each level, so you get this plus n log n. Okay, so let me go a little bit into detail. Actually, how many of you would like to see a bit more detail into this? Because, okay, good. So we will do that because I agree this is a bit rushed. So it's good to do a bit more detail. Okay. So let me start with this recursion, and let's see how you would evaluate from scratch. Okay, but it's important to remember that the easiest way to analyze these divide and conquer algorithms is first write down a clean recursion. Okay. Then figure out what the base cases are. So write down a recursion. And make sure you know what the base cases are. Okay. Once you do this, right, so in the worst case, you can kind of make some guesses, try to prove some running time and so on. Okay. But if you don't do this, you can't analyze the running time anyway. Okay. So that's why it's good to first write down a clean recurrence, which is as simple as possible. And once you have a recurrence, you have all the tricks, right? So that's what you do. Okay. So in our case, we have T of n equals to T of n by 2 plus n. So this T is just a function and it satisfies this recurrence, and I know that T of 1 is 1. Okay. So this is all that, so this is what we need to solve. And how would you go about solving this? So you would observe that, so now you can actually unravel the tree. Okay, so and now you can do it even for more complicated settings. What you will do is, okay, I have T of n. So this is T of n by 2, T of n by 2 plus this n, which is the additional work I need to do. And this again, I can break it up into T of n by 4. Oh, and there's also an n by 2 out here. Oh, this is the extra work that I'm doing. Okay, so I hope it's clear. This one is just n, so this is just work I'm doing at the first step. Okay. So if I'm asking for the total work, okay, so I just need to count these, the work I'm doing at every step. So you could also that term will be negligible. Okay, so there is some amount of time you need to set up this problem of size n by 4. Okay. So in fact, if you were to, if you were to implement merge sort in kind of a naive way, where when you split the array, you actually make copies of it, then setting up a problem actually takes time, which is also n inside. Okay, so it would actually end up with like 2 times n of extra work and so on. Okay, so that's why usually when people think of merge sort, you just pass the indices of the sub-array that you want to pass. Okay, so, and you sort in place. That leads to like the best implementation. Okay, and that's because the setting up time for this iteration itself takes more time. That adds up. Alright, so that's one thing. So that's what you get, and then the next step, so we can observe what's going on, right? So you have 8 copies of T of n by 8 plus extra work adding up to. Okay, so same thing was true here, right? So here you had 4 copies of T of n by 4 plus work of n. The same is true here, and so on. And until when does this tree go? Till the size of the problem reaches 1, right? So it might not always reach 1. It reach 1 only if n is a power of 2, right? But if not, it will reach something small enough. Right? You have to be a bit more careful about how you divide, but yeah, you will still go down to something that is very close to 1. So you will end up with n copies of T of plus extra work of n. Okay, and here I am adding up the extra work in the entire layer. Okay, so this layer will actually have n different leaf nodes. Okay, and yeah, so this is what I need to do. Okay, and yeah, so now what is the total running time? It's actually the total amount of work that you have done. Okay, so run time equals total amount of work we have done. And that is now easy, right? Because the first layer you've done n amount of work, second layer you've done n amount. So it's just number of layers times n. Okay, because in every layer you've done exactly n amount of work. And yeah, and what's the number of layers? This is yeah, what is the number of layers?
Log n.
It's log n to the base 2 times this needs step you have. So this is how you would evaluate a recurrence. Okay, so typically you could have a much more complicated recurrence. We'll see an example of that in a little bit. But this is how you would do it. Okay, so you would write down the tree and try to see how many levels the tree has. In each level, how much work you're doing. Okay, and add up all the work. And as I said, you've got to also be careful about if I am taking too much time setting up the problem, you've got to count that as the extra work. So in this case, I'm not doing much. Okay, so any questions? Yeah.
For our homework problems, are we expected to write down trees in basics?
Oh, that's a good point. I wouldn't want you to go through that. So you should probably just write it down on paper, take a picture or something, and put it in the LaTeX file. Okay. So this is something I would not like to do either. So yeah. Oh, okay. Yeah. I mean, if you really want, you could. You could just write down something like this. Okay, so you could say in the first layer of the tree, there's 4 copies of T of n by 4 plus work of n. Something like that. But if it's easier to draw and take a picture, just do that. So, yeah, handwritten stuff, obviously, make sure it's legible and so on.
Why is the linear log 2n?
Oh, because so every time, so the first step goes from n to n by 2. Next time it goes to n by 4. Okay, and after k steps, it goes to n by 2 to the k. Right? Because first step is 1, 2 and so on. That's the pattern. And you want this number to be constant, right? To be equal to 1. Okay. And that's like saying 2 to the k equals n, or k is log n to the base. So that's
How is that equal to 1?
Sorry?
After k steps, you're saying it's equal to 1.
Right, that's what we want, right? So the base case is just a single element. So that's why you have this n copies of T of 1.
So you don't have to worry about the extra work.
Right, so the extra works are what we are adding up. You don't really have to worry about this inductive thing, because that you will count eventually. So, yeah. So you only add up the extra work. Okay, so in every layer you add up the actual amount of work you're doing. So that's, yeah. Yeah. Because in every layer we observed that the total amount of work you're doing adds up to n. And the reason for that is that in the first step it's n by definition. Okay. In the second step, you have two of these n over 2's. Okay. In the third step, you'll have 4 of n over 4's. Okay, and so on. If you really want to be precise, you should probably write that also. Right? So you'll have 4 copies of t of n by 4 plus so many copies of n by 2 as the extra. Good. So other questions? Yeah.
So when we say extra work, are we talking any kind of sorting or comparisons, anything like that?
So throughout, I'm actually measuring the number of comparisons because, and that's if I want to like literally talk about how many array accesses or something like this, then there'll be a small constant over here. Like I might have to look up something and I might have to do something. Right? So, so I'm talking about number of comparisons here. It's a good point. Yeah. So in sorting, typically we measure the number of comparisons that you're doing between elements. Okay, and here the n number comes because of the merge step. In the merge step, you always compare the heads of these two arrays. Right? And you do one comparison to write down one output. So therefore, since you write down n outputs, you have n squared. That's right. Okay, so yeah. So any more questions before we move? Actually, we can take one. We can take one more, a couple of minutes more break, and we can go to a different example. But meanwhile, I have different questions.
So we usually assume that n is a power of 2 when we do
Yes.
that. So
Yes.
is that okay? I mean, for some other homework problems?
Yeah, so it's perfectly fine to assume n is a power of 2 for basically any problem you encounter here. I mean, there could be other problems where, for instance, it's I have one problem where it's something like this: t of n by 2 plus t of n by 3 plus something. Okay. So here doesn't have that much to assume n is a power of 2 or not. Right? So yeah, so just think of this as if it's not a power of 2, you go down until some point where it's divisible, and sometimes it stops being divisible. Then you have approximately something that's approximately equal to n over 2. Okay? You hope that these functions are continuous enough that if I replace, for instance, if I had 15, right? If I started with 15 in this case, then I can't divide it into 15 by 2, 15 by 2. I've got to divide it into 7 and 8. And 8 is fine, it's a power of 2, but 7 again, I have to divide it into 3 and 4. But you always assume that, okay, I can bound this. I mean, the function value for 7 is kind of close to what it is for 8. Right? You could always bound it like that. And another way to formally say these things is to say, I think of rounding up the n to the nearest power of 2. Okay. Then use it for that. Use that as an upper bound. Okay, because that's only a bigger problem, so it's going to be harder to solve. So that's another formal way to write these things. But generally speaking, between friends, you assume it's a power of 2, do all the analysis. It helps to make n a power of 6, feel free to go ahead. Okay, so up to constants, it's all fine.
What if we did take into consideration the actual time required to break the problem into two parts at each level?
Yeah, so
it will be like a geometric series: 1 plus 2 plus 4 plus 8.
What do you mean the actual time to break the problem?
Like at the first level, you are breaking the problem into two parts, and the next level it becomes 4 parts.
Yeah.
Next level becomes 8 parts. So there's also time required for that also.
Right. So you can actually fold that into the recursion in all these things, because you say that it's 2t of n by 2 plus n plus 1. Okay, that plus 1 goes into breaking the problem. Right? And the first step, so that's the nice thing about writing a recurrence in the clean way, because you can actually look at exactly what all steps the algorithm is doing. Every step you've accounted for. Right? And the recursive step happens in the recursive step. You don't have to bother about it in this current test. So that's, yeah. And that's a good question. If you solve this recurrence also, you'll probably get a plus extra n factor. Okay, but that's a lower order term. Good. Anything else? Yeah.
In problems like where the division of the parts isn't fixed, as in here we are dividing it into two parts, then again into two parts. But where that division is not fixed and the things are like random, then how do we go about finding the random?
Right, so that's a good point. We'll see an example of that somewhat later in the course. So, let me see if I can find some space. Yeah, so you could have problems in which you have, for instance, do you mean something like literally random or something arbitrary?
So it depends on the values, that's how the division
Yeah,
is.
so there are many problems in which when you do divide and conquer, it's not, you don't literally do it into n by 2 and n by 2, but maybe, so here's another way of doing sorting recursively, right? So you could say I have a big array, you could say I pick some element of the array and I divide this array into two pieces. So let's call this element x. This is the subarray of elements less than x. And this is subarray of elements bigger than x. In this case, what she's saying exactly happens, because if x happened to be kind of the median of the array, then okay, you actually get two equal halves. Okay. But if x is not, then you might actually get something where you have n over 3 here, maybe 2n over 3 on the other side. Okay. And now your recurrence becomes something else. And what's worse, sometimes you might not know where this x is. You might just have a rough bound. So, yeah, so things like this will, yeah.
Not only that, means in the next step, this n by 3 and 2n by 3 is also not fixed, it would change.
Yes, that could change differently as well. But the nice thing is that you can always still write it as a recurrence, right? Because now your t of n, so what she's I guess kind of implying is, what if I choose x to be a random element? Okay, so then I can only talk about the expected value of the running time. Okay, so t of n then turns out to be a random variable. Okay, so this is something that depends on which x I chose. Right, so it's actually a random variable. And I can only talk about the expected value of this t of n. And we'll see such analysis in the future. But this is actually a great point. So sometimes recurrences are not always this clean. In fact, in reality, they are almost never that clean. Okay, so yeah, so you've got to be wary of this. And yeah, and that's why there's no single method to really solve recurrences. Okay, so I pointed to this book, which is a nice source. This book of Lehman Layton. So these guys have a couple of good chapters on how to solve recurrences. And really the only right way is what they call this plug and chug method. You guess the answer, plug it in, work through the calculations, right? So they have a nice term for this. So yeah, so that's how you mostly solve these kind of things. Okay. So and that's how you can do this case also. Turns out. So yeah, but this one is called quick sort. We will see this later in the course. Okay. Any other questions? Okay. So this is a good point. Okay. So I wanted to show another example where it's perhaps not very clear that you can do divide and conquer. Okay. So that's this case of multiplying two n-digit numbers. Okay, so what does it mean? We all know how to do this, right? So we know how to do this in school. You have two n-digit numbers, okay, and you write them down nicely, one below the other. So how do you do this? I have 2 n-digit, yeah.
Split into high and low order bits and then do the 4 combinations.
Yeah, so you multiply that number by bn first. Okay, so you'll multiply by this guy first. You'll write something, just C1, C2 to C, could be Cn or Cn plus 1, depending on, there could be 1 digit here, carry digit here. What you did. And then you shift it, you write some D and D and something. And then finally you add these up. Right, so this is what we've all hopefully learned in school. So how long does this take if I have 2 n-digit numbers? Let's assume everything is base 10 for now. Okay, and why is that?
Every digit with all the digits in.
Yeah, so this step takes n, computing this guy takes n time and so on. And the adding also takes n for every thing. Okay. So it's like n, it's basically n squared. Okay, so it's n squared for coming up with these rows and n squared also for adding. So it's something like that. So overall it's O of n squared. Okay, so now the question is, can we do better? Okay, so how many of you have seen how to do this better? Smaller than I thought, but okay. So let's see how you can do this better. Okay, so this is an example in which you don't ordinarily think of divide and conquer, right? So I have 2 n-digit numbers. How am I going to find that product? Because the product requires literally like looking at multiplying each number with every other thing. That's what you would guess. So it's rather surprising that you can actually do something. Okay, so let's try to do it. But if someone were to say, okay, try using divide and conquer anyway. Okay, so then what you would do is, so this is what I call force divide and conquer, right? So I have 2 numbers. I'll call this A. I'll call B to be this, and both are n digits long. I could say, okay, I will break A into X, Y. I will break B into 2 n over 2 digit numbers. Let's call them, I ran out of all letters. So C and D. And okay, so these are 2 n by 2 digit numbers each. So what is A? So I want to write A times B in terms of X, Y. Actually, let's call this U and V. Okay, so there are cleaner letters. So how would you write A times B in terms of X, Y, U and V? First let's start with how would you write X in terms of, A in terms of X and Y. Somebody who hasn't seen this.
What is M?
Sorry?
M is the number of digits.
Yeah, so sorry, this is actually n. So this is these are n by 2, n by 2.
Okay.
Yeah. Both of these are actually n. Yeah. So
X 10 raised to n plus 1.
yeah. So you're saying A plus Y.
N by 2, sorry.
Right, so it's the number of digits. So this number is basically X followed by n over 2 zeros. Okay, and to that if you add Y, then you get X concatenated with Y. So that's A. Once you have such a representation, now we know how to do this, right? So this is X times 10 raised to n by 2 plus Y times U times 10 raised to n by 2 plus V. Okay. These are just sum of 2 terms, so I can multiply these well. That's 10 raised to n times xu plus 10 raised to n by 2 times e plus y. Sorry? Y plus b. xv. Right? Because you got to pick one term here and the b. Okay, so because it's 10 to the n by 2 plus y times b. Okay. So this is already looking in decent shape, right? So now I can try to do divide and conquer. Because these are just products of n over 2 digit numbers. Okay, so I can try to do divide and conquer over here. So suppose I computed x times u, I computed y times u, these four products. Okay. Then how much time would you need to come up with a times b?
Log n.
Log n.
What was the question?
So the question was, it was basically, suppose you knew all these four products.
Yeah.
Okay? So how much time would it take to compute this whole expression? It's some constant times n, right? Because I know this, and all I'm saying is start with xu, which you know, pad n zeros. I'm doing basically an addition of four numbers, each of which is at most 2n digits long. Okay, so this is like addition of four numbers, 4 integers, each 2n digits. So these I can write down in long form and use the elementary school algorithm again. Right? So this takes over n time. Okay, so what we have written is, so if you call t of n the running time for an instance of size n, then I'm saying that this way of doing things, so t of n is 4 times t of n over 2 plus O of n. Okay. Okay, so this looks reasonable, but what would this, what do you guess this would end up solving to? You might guess n log n, but it will not end up working that way. Okay, so because it's 4 times t of n over 2. Okay, it's not, so earlier we said that if it was 2 times t of n by 2 plus O of n, it's n log n. So now it's much more work. So that's like saying in this tree, you have 4 things of size n by 2. Okay. And so I'm not going to go into this, but you can prove that this actually solves to n squared. And the reason, it's actually very easy. So what you will do is, it's like n plus 4 times t of n by 2. And then you will say that this is like n plus 2n plus 16 times t of n by 4. You will observe that you will have essentially 2 to the 2k out here, which is like 4 to the k times t of n by 2 to the k. This will be like the kth term. So if this becomes 1, this becomes n squared. Okay, because 2 to the k will be n, 2 to the 2k will be n squared. Okay. So I won't do this, but this is a very simple exercise for you to do it, and this turns out to have solution n squared. So yeah, so this is actually the way some practice for you to get to just do that at all. So recurrences again, I would say don't be afraid, right? So somebody used to say that,
Why is there the O of n in this recurrence? Because addition is constant.
addition takes constant time if you have constant bits, but if you have n bit numbers, literally have to go through. Yeah.
Can we directly write master theorem like in homeworks or something? Can we write solution O n square using master theorem?
Yeah, so okay, sorry, yeah, this is something I should have mentioned. So there is something called this is a very grand name, so I don't introduce it. There is something called a master theorem. Okay? So it's actually a pretty restricted theorem. What it says is, if you have recurrences of the form t of n equals some constant times t of some n over p plus some function, let's call it t of n, gives you a general expression for things like this. Okay? But as she was pointing out, this requires really equal sized pieces and a of them and things like this. Okay? So yeah, so it's called master theorem. It's actually, you can derive this very easily. So that's why I don't usually introduce it, because for any recurrence worth its salt, you won't be able to apply master theorem. So okay, so we have like a few minutes left. So I'm going to tell you a rough idea of how we can do better. Okay, so it might seem that this is n squared and this solves to n squared. Our elementary school algorithm also was n squared. So is divide and conquer giving us anything? Right, so that's what you might wonder. Because even after you do this whole observation of breaking up into pieces, you're still taking n squared time. So now the question is, can I actually find these 4 products that I need to find using fewer than 4 multiplications? Okay. And if I did 4 multiplications, I would get 4 times t of n by 2. If I could do it with, let's say, 3 multiplications, then I would only get 3 times n over 2. Hopefully that solves to something better. Okay. And that's the idea of what is called this Karatsuba's algorithm. Okay, so the question is, can we find the quantities? Remember what we want to find, right? We still need to find 4 quantities. So the first guy is x times u, xu, yu, and yeah, so I intentionally wrote it down this way, that these are the quantities that you really need to find, right? Because the final answer is this times 10 to the n plus this times 10 to the n by 2 plus this. Okay? So I don't literally need you to find yu and xv. All I need is the sum. Okay? So there's some clever way in which I don't compute these quantities individually, and somehow I can do all of these 3 quantities. Then there's a good way of, I mean, then I would be in much better shape. And this is what Karatsuba had observed. Okay, so since we don't have time, I won't go into how you get this, but this is a very simple algebraic manipulation. Okay, so it turns out by just computing things of the kind x plus v times y plus u, if I'm not mistaken, and the other one. Okay, and one of these. Okay, so the details are actually not so important, so you will find this in a bunch of textbooks. But the point is that you can do this with just 3 multiplications. Okay, so 3 multiplications of n by 2 with digits, numbers. Yeah. Did you have a question? Somebody here had a hand up. Okay, all right. So actually, I don't want to also go into the details, because in your homework you'll see how to generalize this. So you'll actually see how this kind of a reasoning comes from. Okay. So the last problem in the homework asks you to generalize this, and there I asked you to break it up into 3 different pieces. But think of doing the homework exactly with 2 pieces and you get this. ends up with is a recurrence of the form T of n equals 3 times T of n by 2 plus O of n again. And this one, you can solve it the way I was trying to solve before. Now you say that this is 3 squared times T of n by 2 squared plus 3 times, okay, let's assume that this O of n is actually just n. So then you get 3 times n by 2, then you will get 3 cubed times T of n by 2 plus 3 squared times n by 2 squared. Okay, so this is another way in which you can just write down what's going on in the recurrence. I'm just like expanding it out one layer after layer. So these are basically the terms that would show up in the tree, right? So I'm just writing it out as 1 plus the other. And if you observe, what you will get is that this thing solves to T of n equals n to the log 3 to the base 2. So this number is weird, but it's it's better than x squared. And the reason for this is just this, that after k steps, essentially you will get 3 to the k times T of n by 2 to the k. Okay. And you want this quantity to be 1, which means k has to be log n to the base 2. Then you will have, so the overall running time is 3 to the power of log n to the base 2. Okay. This looks odd, but if you simplify it, this is exactly equal to n to the power of log 3 to the base 2. So if you guys remember how you manipulate logs, this is exactly what that is. So 3 to the power of log n to the base 2 is exactly n to the log 3. So this, so it's just basic manipulation. So it's not very important, but what you should, the exact bound is not very important, but what you should observe is that this is actually strictly less than n squared. Okay, so this turns out to be something like n to the 1 point, anyone remember this? 5.8? 5.8. Okay, so this is actually significantly better. Okay, and so it turns out you can bring this down further. Okay, so in the homework you will see how to bring this down to n to the 1.45 by breaking up into 3 pieces. You can actually keep doing this. You can break it into smaller and smaller pieces. So in the first class, somebody had asked if there are problems where dividing it into smaller and smaller pieces gives you more of an advantage, more and more advantage. This is one very nice example of that. So let's stop here.